In our study of complex numbers, let's look back at history, all the way back to the 1500s. Back then, mathematicians were looking for a way to solve a cubic equation, similar to the quadratic formula, where you would have a formula that you could just plug in coefficients and it would give you an answer. But back then, mathematicians' lives were very much like soap operas, where there were math duels and competitions to see who was the best. They would steal each other's work to prove that each was the originator of a solution. So two gentlemen, Tartaglia and Cardano, were two that they competed back and forth, and really they were looking at a way to solve a cubic equation. And Cardano, right here, is the man who is credited really with that first look of complex numbers. So as Cardano was trying to solve these equations, he was finding that he was getting answers that really didn't make sense with the current number system. Remember, back then, they only had positive and negative integers and rational numbers, both positive and negative. So they needed a new way to look at a problem similar to this. X squared minus 3x plus 10 equals 0. I know this is a quadratic, but what happens when we try to solve it? We get a 3 plus or minus the square root of negative 31 over 2. And we've been saying that when your discriminant is negative, you have no real solutions. And that's true, but mathematicians still needed a way to use something that would represent a number like this. And the trouble we're looking at is that this is saying x squared is equal to a negative 31. In other words, what number times itself is equal to negative 31? We know that a positive times a positive is positive, and a negative times a negative is positive. So how can we get a negative number? So what Cardano did is he just created it. He said, let's assume the square root of negative 1 exists. If that's true, that means we could take the square root of negative 31 and rewrite it as the square root of negative 1 times the square root of 31. And then if we needed to simplify the square root of 31, we could. And if we do this and break up our negative square roots in this way, we actually get numbers that behave and follow the rules of algebra that we've been using all this time with real numbers. And this led to an extension of the real number system. And that's called the complex numbers. So a complex number is any number of the form a plus bi. A is the real part, and bi is the imaginary part. So a number like the square root of negative 4, that could be rewritten as the square root of negative 1 times the square root of 4. And we know that the square root of 4 is the same thing as 2. And over time, this idea of the square root of a negative 1 became so common, it was replaced with the letter I. So that's what I stands for. It is the square root of negative 1, which means we can simplify this to 2i. If we look at one more, how about the square root of negative 27? That we could rewrite as the square root of negative 1 times the square root of 27. We could then simplify that, square root of 27, into 3 square root of 3. And finally, we could change this to 3i radical 3. So the same rules of simplifying radicals holds under this new number system. And in fact, every real number we know falls into this idea of a complex number because the b for the imaginary part would just be 0. For example, how about 312, right? We could write that as a complex number by saying it's 312 plus 0i. So the real numbers that we have been working with are really all part of the complex numbers. So now let's really look at what complex numbers are. So here is our expression, a plus bi. A and b are both real numbers, and I, right, is from I squared equals -1, and that's your imaginary part. It should make sense because if I is equal to the square root of -1, if we square both sides, we'll get I equals -1. So look at these examples right here. If we're looking at 3 plus 4i, 3 is the real part and 4i is the imaginary part. For 6i, the real part is just 0, right? You could write this as 0 plus 6i. And then how about -7? -7 is a real number, but we could still write it as a complex number as -7 plus 0i. So they all fit under this idea of a complex number. And remember, Cardano and the other mathematicians found that the algebra of complex numbers was the same as the algebra of real numbers. So when we're adding complex numbers, like a plus bi plus c plus di, we're going to add the reals together and then add the imaginary parts together to get our answer. The same thing will happen with subtraction. Subtract the real parts and then subtract the imaginary parts. And for multiplication, the same rules follow. We want to FOIL, right? First outers, inners last. Then we're going to combine terms together. The real terms will get combined and the imaginary terms will get combined. So for example, how about if you had 3 plus 4i minus 2 minus 5i, right? Just treat the i's like variables. So here we are going to combine the reals, which would be 3 minus 2, and then combine the imaginary. We've got a plus 4i. Don't forget this gets distributed just like it normally does, plus 5i. And if we combine, we'll get 1 plus 9i. And how about if we're multiplying? Let's say we have 2 plus 3i times 2 minus 4i. Now there's one thing to be careful of. Now we can FOIL this just like we normally do, and we'll get what? Our firsts will be 4, our outers will be minus 8i, our inners will be plus 6i, and then our last will be the 3i times the 4i, and there's a negative sign there, so that will give us 12. I times I is I squared, and here's where the something different happens, right? What is I squared? Remember way back here, what's I squared? It's the same thing as -1. So this can get replaced with a -1. So that means we actually have 4, our minus 8i and our plus 6i can combine to be -2i. And that last term now we have a -12 times a -1, which is a plus 12. And that's going to leave me finally with 16 minus 2i. So remember, when you're multiplying, look for that I squared, and remember it's -1 because that will pop up again and again. So we've talked about adding, subtracting, and multiplying complex numbers. So what's next? You guessed it. Let's look at dividing complex numbers. When dividing, it's going to be really similar to when we rationalized denominators when we had radicals. Remember when we had something like 3 divided by 2 minus radical 5? Remember, we would always multiply it. To rationalize it, you multiply it by the conjugate, which is 2 plus radical 5 and then 2 plus radical 5. Well, the same thing or something similar happens with complex numbers. For complex numbers, we're going to multiply by the complex conjugate, right? So notice here we've got c plus di. We're multiplying it by c minus di over c minus di. So in this first example here, A, we have our denominator is 1 minus 2i. Usually we use the number z or the letter z to represent complex numbers. So we can say if z equals 1 minus 2i, then the way to write a complex conjugate is called z bar with that little line up top. The complex conjugate will be 1 plus 2i. And so if we multiply this by 1 plus 2i over 1 plus 2i, again, notice I'm still just multiplying by a form of 1. I'm not changing this expression. And now to solve these, we want to FOIL our expressions, right? So the numerator, we're going to get 3 times 1 is 3, plus the outers will give us 6i. 5i times 1 is plus 5i for our inners, and then our last will be 5i times 2i, which combine everything, we're going to get plus 10i squared. And remember, what is I squared? It's the same thing as just a negative 1. So our numerator, in fact, will be 3 minus 10, right? Because the 10 and the negative 1 becomes a minus 10. That'll be a negative 7. And our 6i and our 5i will be plus 11i. Right, so again, remember that trick, which it's not really a trick, it's a rule, that I squared becomes a negative 1. For the denominator, we can also FOIL this, or if you see, it's a difference, so our outers and our inners will cancel. So we really can just think about doing our firsts, which will be 1 squared, our outers and inners will cancel, and then we'll be left with a negative 2i times a positive 2i, which will be a negative 4i squared. And again, remember, the I squared is just negative 1. So we have a negative 4 times a negative 1, which really is just a plus 4. So my denominator will be 1 plus 4, which is 5. And remember, a complex number is written as a plus bi. So you want to separate the real and the imaginary part, which means then we shouldn't leave our expression as this. We want to write it as negative 7 fifths and then plus 11 fifths I. And that's going to be your final answer. So let's look at this next problem here. We've got 4i in our denominator right here. And again, we don't want to have I in our denominator. You can think, we want to multiply it by its complex conjugate. You can think of 4i as 0 plus 4i. So its conjugate would be 0 minus 4i, or just minus 4i. So we're going to multiply this by negative 4i over negative 4i. Again, I'm still only multiplying by a form of 1. Now to do our basic rules, our numerator, let's distribute that. 7 times negative 4i will be negative 28i, and our plus 3i and negative 4i will be negative 12i squared. I'm just going to continue this across, and our negative, remember our I squared will be negative 1, so this really is a negative 28i plus 12. And our denominator, we have 4i and negative 4i. That's going to be 16 and negative 16i squared. And again, that I squared just becomes 1. So our denominator will be a positive 16. And if I rewrite this and simplify, we'll get 12 over 16, which is 3/4. I put the real part first. And then minus 28i over 16 is 7/4 I. All right, one more thing left. When dealing with square roots of negative numbers, you need to change to the imaginary way first before doing any sort of simplification or operations. What do I mean by that? If you have something like the square root of negative 2 times the square root of negative 3, you want to change them first, right? Remember, the square root of negative 2, we can rewrite as I square root 2. It helps to keep the I in front, right? Not behind the radical, because sometimes then it gets lost inside the radical. Our radical negative 3, we want to rewrite as I times 3, which then would become I squared times the square root of 6, which would be a negative square root 6. And that should make sense, because if we think about this, right, the square root of negative 2 is really the square root of negative 1 times the square root of 2, and 3 is the square root of negative 1 times the square root of 3, and if we multiplied the square root of negative 1 times the square root of negative 1, that's where that negative sign is coming from. Right, so this does work out to be the negative square root of 6. Don't fall into the trap of saying, oh, I'm just going to multiply these straight out and get the square root of 6. That is a no-no. Change it to its imaginary form first. Next class, we'll practice these operations of complex numbers, and your next video will be looking at a geometrical version of I.